Hi everybody. Previously we talked to you about the interface system. For this tonight we will talk about the multiphase system. We talk vapor liquid mixture, vapor gas mixture, something like vapor solid, liquid solid mixture, which is important in the chemical plant and petrochemical plants. Right? First of all, we would like to talk to you about the phase diagram, which I think you studied in the thermodynamics already. For this case, we will show you how to change from vapor to liquid, from liquid to vapor. Right. Okay, this is the phase diagram. These are P and T diagram, pressure temperature diagram. Right. This is for water and this is for carbon dioxide. We have the cylinder and piston, that's right. The piston, if you compress the piston, you compress the vapor, the volume of vapor, water, that will decrease until you reach some point, the vapor will change to liquid phase. Right. And also if you expand or you reduce the pressure, at some pressure will change from liquid to gas phase. Okay, for the first step we consider the vapor as point A, something like this. This point A, we stay at 20 degrees Celsius, that's right. 20 degrees Celsius. Okay. Before of this, we talked to for the P and T diagram. For P and T diagram, y-axis we talk about the pressure. X-axis is temperature. We have three components, three phase. That's right. Solid, liquid, gas phase. That's right. This is the equilibrium line for solid, liquid. This is the equilibrium line for gas. Solid is the equilibrium line for vapor and liquid. Okay. If we consider at point A at 20 degrees Celsius and about 3 millimeters mercury. Right. Okay. After that, for this case, we have the vapor, and then you compress the piston. You compress the piston, the pressure increase. That's right. Okay. Pressure increase until point B. Okay. The pressure increase until point B. Right. There are some liquid and vapor. Because point B is the equilibrium line between liquid and vapor. For this case, is the liquid and vapor stay at equilibrium. Stay at equilibrium. Okay. If you we call point B is the boiling point. Sorry, is the dew point or the condensation process. Because we change from vapor to liquid, we call it is the condensation from the liquid from vapor to liquid. At this point, we call dew point. The first droplet of vapor that's changed to liquid, we call this point is the dew point. The temperature at this is the dew point. Right. The pressure is the pressure at dew point. And then if you compress further, then you compress further. Like this, you compress further until the pressure is higher than at point B is about 17.5, something like this. All of vapor will change to be liquid like this on this point. Right. On this point, the point above point B, all of vapor change to be liquid. And then you get compressed further until point C. That's right. Point C, you increase the pressure, but from point A, B, C, you still constant temperature. That's right, self temperature. But pressure increase, it change from vapor to liquid. This is completely change. Okay, for this case, you stop to decrease the piston or increase the pressure. And then from point C to D, you try to increase temperature. Okay. For this case, you have liquid, and then you increase temperature. That's right. Increase temperature at constant pressure. You increase temperature, that's right, until this point D. This point D. What does it mean? This point D. Point D, if some molecule or the first bubble of liquid occur, we call this point is the boiling point. The process is evaporation. That means liquid change to vapor. The first point that bubble occur, we call it is the boiling point. Right. The boiling point is occur at 100 degrees Celsius at 760 millimeters mercury. We call this normal boiling point, something like this. Okay, this boiling point. And also if you increase temperature further, because you increase temperature, volume will increase, right? Because from liquid to vapor, volume of this is increased until it's oily, you get some bubble vapor, and then you increase temperature further. If the temperature greater than 100, or of liquid water is changed to vapor, right? It changed to vapor, right? And then you increase to 130, you get all of it vapor. For this process from A to E, we have to process as A to B, we get the dew point or condensation, and B to C, complete condensation. C to D, we get the bubble point, because this is the vaporization. And to E is increase the temperature further, you get all of liquid to vapor, or vapor to liquid. For this case, that's right. From vapor to liquid, we call the condensation. At point the first droplet from vapor to liquid, we call this the dew point. Okay, dew point means temperature at the dew point or pressure at the dew point. And then you increase temperature. The first bubble occur in the liquid, we call this the dew boiling point. Process is evaporation. Okay. From liquid to vapor is evaporation. From vapor to liquid, we call is the condensation. Okay, if you consider the solid and liquid, right? For example, if you start at this point, that's like if you increase the temperature of solid until this point, from solid to liquid, we call this is the melting, right? Melting point. This is from the solid to liquid, we call this melting point. The melting process from solid to liquid. And also the opposite from liquid to solid, we call the freezing point. From the freezing point. From liquid change to solid, from the freezing point. And also from the solid to vapor, that's right, we call sublimation. Right? Sublimation. Or some vapor change to solid, we call the deposit. Some vapor is deposit to the solid, something like this. Okay, the most common we have to talk like the evaporation, condensation, condensation from vapor to liquid, evaporation from liquid to vapor, melting is solid to liquid, and freezing liquid to solid, and sublimation is solid to liquid, solid to vapor, solid to vapor. And also for this is for the water. This is for the system of carbon dioxide. Carbon dioxide. Carbon dioxide. This the diagram it should be there are some different. That's right. Okay. Moreover, in this point, there are some triple point. Triple point mean solid, liquid, and vapor occur or stay at the equilibrium. But we have three components: solid, liquid, and vapor. And also, if you increase some pressure or temperature until you get the critical point of liquid and vapor, we call it the supersaturated fluid. Right? The fluid as above critical point, we call the supersaturated fluid. But that's key. This is, I talked about already, right? The vapor pressure. Vapor pressure is the pressure of the vaporization. That's right. Pressure that corresponding to the point vapor liquid equilibrium curve. We call this the vapor pressure. Or vapor pressure, or the pressure at boiling point. Boiling point means temperature at boiling or at evaporation. And pressure at boiling point, we call this vapor pressure. Mostly for water, the other liquid, the normal boiling point, we call the boiling point as 1 atm. Right? Boiling point is 1 atm. And also melting point, freezing point, I talked to you already. And sublimation point, right? Melting point is from solid to liquid, or freezing point from liquid to solid. Sublimation from solid to pressure. And triple point mean the three phase, right? Solid, liquid, vapor phase are all exit in the one point. And the critical point or supersaturated are supercritical fluid, which means the temperature and pressure greater than critical temperature or critical pressure. We call this the vapor liquid equilibrium. We call this super fluid, right? superheat fluid. Okay. The next step, we talk how to measure or how to estimate vapor pressure. So if we talk about the vapor pressure, we talk about the volatility. Volatility is the property of liquid or substance that can be evaporated. Right? We call it the degree of volatility. Volatility is the degree which species tend to transfer from liquid or solid to the vapor state. At given temperature and pressure, a highly volatile substance is much more likely to be a vapor than substance is low volatility. That means high volatility means substance love to vaporize, right? And all it's more likely to be the vapor than the low volatility. For example, if you talk about distillation, the distillation we use separate like the crude oil to be like the gas phase or gas methane or the benzene, kerosene, diesel, wax, something like that from the distillation. Distillation, the separation unit is very important in chemical and petrochemical plant. That's like it based on the difference in vapor pressure. That's also if you talk about the volatile species. Okay. It is used to separate more volatile species from less volatile species by partial vaporization of liquid mixture. Okay, back to the vapor pressure. The vapor pressure of P star of species is a measure of its volatility. Right? It used to measure the volatility, high vapor pressure or low vapor pressure. High vapor pressure is okay. It leads to vaporization. The first technique or the first equation that we use to estimate the vapor pressure, we call it Clausius-Capian equation. Right? The Clausius-Capian equation is log vapor pressure equal to minus delta SV divided by RT plus B. This is the formula to estimate the vapor pressure, which is a function of heat of vaporization or latent heat of vapor. You get constant temperature and constant B. This evaporate or estimate from the experimental data. Right? If you have the experimental data, right, you know the vapor pressure, you know the temperature, you can evaluate the latent heat of vaporization. Right? If you plot log vapor pressure versus 1 over T, get slope is minus delta SV over R, right? And intercept is B. It's straight line. Okay? And another equation is Untitled equation is a famous equation that used to evaluate the vapor pressure. Only this obtained from the experimental data. It's log vapor pressure equal to A minus B divided by T plus C. A, B, C is the constant evaluated from the experimental data. T is in temperature is in Celsius and P is in the millimeters mercury. I show you this table. The Untitled equation is Untitled equation. P is millimeter mercury. T is Celsius. The vapor pressure calculate if you know ABC. ABC you can erase from this. Acetaldehyde, right? The formula and the length. You can use this. You can calculate the vapor pressure during this length of A, B, C. Okay. For example, if you calculate acetaldehyde at 25 degrees Celsius, this is temperature. For A value is this is A value, right? This is B value, and this is C value. Okay. Log vapor pressure of acetaldehyde equal to A minus B divided by temperature is 25 plus C value is equal to 2.9551. And then you anti-log, that's right, take anti-log. Vapor pressure equal to 10 power 2.9551. You get 902 millimeter mercury. Okay. You can evaluate, that's right. You can interpret the vapor pressure from this table, or you can interpret from this formula if you know like the heat of vaporization, and you know B, you can evaluate something. This I show you only two equations that you to evaluate the vapor pressure. Or if you can use like some graph or some figure, the figure that show you the y-axis is vapor pressure in pound per square inch. It's vapor pressure, and temperature in Fahrenheit. And there are lots of chemical species like ethylene, carbon dioxide, ethane. You know temperature, you can calculate vapor pressure. You know vapor pressure, you can calculate temperature. This is the boiling point. That's right. Or dew point, something like this. These are Koch chart. That's right. The Gibbs phase rule. Right? How you know the Gibbs phase rule? Read the variable that describe the condition of a process system for into categories extensive property or extensive variable and intensive variable. Extensive means the property that depend on the size of the system. Intensive means the variable that do not depend on the size of the system. For example, mass and volume. Right? Mass and volume depend on the size of the system. It's an extensive property because it depends on the size of the system. Okay, for the intensive variable, for example, temperature, pressure, density, specific volume, mass, and mole fraction. So if you talk about the density, pressure, or viscosity of water, water with 10 cubic feet of water, 20 cubic feet of water, at the same temperature, is the same density. It's not depend on the size of the system, for example. And also for this case, the number of intensive variable, we will talk about the number of intensive variable that can be specified independently for a system at equilibrium. We call degree of freedom. We call this Gibbs phase. For this case, for example, the Gibbs case rule, we have two Gibbs phase. Through degree of freedom, we have you require two intensive property. You can calculate vapor. At one, this 1 degree of freedom, and calculate the vapor pressure. For example, how to calculate degree of freedom? Degree of freedom, that's right. We calculate based on equal to 2 plus C. C is the number of chemical species minus pi. Pi is the number of phase in the system at equilibrium. This is important because if we would like to know some variable, you have to know at least degree of freedom that talk about the intensive variable. For this chart, if you would like to know the vapor pressure, you have to know at least one intensive property or 1 degree of freedom. This means temperature. You know temperature, okay, you can evaluate vapor pressure. Let's get it for example. Example, determine the degree of freedom for each of the following system at equilibrium. Okay, for the first one is pure liquid water. Pure liquid water, we have one phase and one component. That's right. One phase is pi equal to 1. Component equal to 1. So degree of freedom is 2 plus one component minus one phase. You get 2 degree of freedom. That means you have two intensive variables must be specified to fix state of system. For example, you have to fix temperature, pressure. That's right. Or you have specified density or viscosity. For this case, if you would like to know some property, you have to specify only two property. You have to specify temperature. You specify pressure. Okay, you can calculate viscosity or density, for example. For the next step, if you have a mixture of liquid, solid, and vapor, water. For this case, we have one component is water. But at equilibrium, we have 3 phases, liquid, solid, and water. Okay. For this case, 2 plus 1 component minus 3 phase equal to 0. But it is not necessary to specify the intensive property. This means the triple point. That's right. Triple point is not necessary in this case. And the next example, vapor liquid mixture of acetone and methyl ketone. In this case, we have 2 components. We have acetone and methyl ketone. And we have 2 phase, vapor and liquid. Okay, degree of freedom is 2 plus 2 components minus 2 phase. We get 2 degree of freedom. For this case, if we would like to know the property of liquid vapor mixture of acetone and methyl ketone, you have to specify at least 2 intensive property. Mostly we specify temperature, pressure, right? And then you can calculate mole fraction of where acetone of methyl ketone in the mixture, something like that. This for example. Okay. The next step, talk about the gas liquid system. Gas liquid system for one condensable component. For this case, we have the gas liquid and only one component that can be condensed. This is more important in the evaporation of drying or humidification. Evaporation, you operate like you would like to concentrate. Right? You have to evaporate some solvent. For solvent is evaporate out, okay, the concentration is increased, something like this. Or drying, you have to evaporate all of liquid solvent out of the solid, something. Humidification. Humidification also, you would like to humidify the system. When you would like to condense some water, you have to mix water and air to be the humid air, something like this. Or dehumidification or condensation. Condensation, we would like the vapor to liquid, right, to gas to liquid. Opposite to vaporization. Dehumidification means you have to write to express out of some liquid in air. It's opposite humidification. Humidification, we would like to mix some water in there, right? But dehumidification, we would like to de-water out of there. This is the important application of gas liquid system. That's right. For gas liquid system, the first rule that is the most common is law for a single condensable species. As if a gas at temperature pressure contain a set vapor, the set vapor mole, the Yi is the mole fraction of vapor. This mole fraction of vapor is equal to mole vapor divided by mole total gas. Right? If this vapor is the only one species that can be condensed. Like for this one condensable, if the temperature was slightly lower than the partial pressure of the vapor equal pure component vapor pressure. Because this is the law. The law is, for this case, partial pressure equal to vapor pressure of the pure species, pure vapor. That's right, with equal to YIP for this case, YIP. Okay, but that means that a gas in equilibrium with a liquid must be saturated with the volatile component. Partial pressure of vapor at equilibrium in a gas mixture containing a single condensable component cannot exceed the vapor pressure of the pure component. If Pi equal to P star, that means partial pressure equal to vapor pressure. The vapor is saturated. Yes? And then you attempt to increase Pi by adding more vapor, gas phase, or by increasing the total pressure. It must be condensation. Okay. The next step, we would like to talk about the superheat vapor. Right? If a vapor present in a gas is less than its saturation amount, a vapor present in a gas less than saturation amount, we refer this as a superheated vapor. So what does it mean? If YIP less than Pi star, less than vapor pressure, we call it the superheat vapor. Right? Okay. And if a gas containing a single superheat vapor is cool, if the superheat is cool as constant pressure, the temperature at which the vapor becomes saturated from the superheat, and the superheat is cool, and the temperature at the vapor saturated with liquid, we call this point at the dew point of the gas. And this means for law is Pi equal to YIP equal to Pi star. That's right for this case. Okay. But that's, we can calculate the difference between the temperature and the dew point of the gas. We call the degree of supersat, or degree of superheat. Sorry. The difference between the temperature at vapor pressure of superheat, the dew point, this is we call the degree of superheat. That's it. Okay. I will show you how to use this relation to calculate the degree of superheat, to calculate the dew point or power point. For this case, a stream of air at 100 degrees Celsius and 5,260 mm mercury contain 10% water by volume. First, calculate the dew point and degree of superheat of the air. Second, calculate the percentage of vapor that condense and the final composition of the gas phase. Okay, for this case, if you cool the system, from 100 to 80 degrees Celsius at constant pressure. Then calculate what percent of vapor occur due to the condensation. Right? The third one, calculate the percentage condensation and final gas phase. If instead of being cool, right, the second we cool the system, but the third we did not cool, we compress. Compress means increase the pressure. Right. If I show you it the first two slide, if you compress the pressure until it dew point, it will be from vapor to liquid also. The fourth one, assume that the process of pass-through is like the product gas is analyzed and the mole fraction of water differ from the calculated value. What would be responsible for the display between calculated and measured value with the difference with the error between the calculated and measured value. Okay, step by step. Okay, the first one, calculate the dew point and degree of superheat. For this case, you can calculate like the fraction, right, and partial pressure of the air. For this case, you know, right, the partial pressure of water in air, right? Partial pressure is equal to fraction of water multiplied by total pressure. That's right. The fraction is 0.1. Pressure is 5,000. That's right. You get 526 millimeters mercury. Okay, and then you calculate or you can interpolate from the table, right, by the boiling point or the point of water as 100 degrees Celsius. 100 degrees Celsius, the normal boiling point is 760 millimeters mercury. For this case, the vapor pressure, right, vapor pressure is higher than partial pressure. From this case, vapor pressure is higher than partial pressure, that is equal to IPI. This means a superheat system. Right? In this case, the state at 100 degrees Celsius, and this is the superheat system. The vapor is superheat. But at this system, the partial pressure is 626 millimeters mercury, but your vapor pressure of water at 100 degrees Celsius is the vapor pressure is greater than partial pressure. We call it superheat vapor. Then you can calculate the degree of superheat. Okay. First case, the partial pressure equal to vapor pressure equal to 526 millimeters mercury for this system. And then you can calculate the dew point temperature when the vapor will drop to the liquid, right, for this pressure. You can open from table B3. This is the vapor pressure side. You know, right, the pressure side is about 526. We approximately is about 525.76. The temperature is 90. This does mean dew point is 90 degrees Celsius. For this system, 90 degrees Celsius. Okay, how to calculate the degree of superheat? Because the system at 100 degrees Celsius. But for this case, the vapor with it drop to the liquid at 90. This means 10 degree of superheat. 10 degree of superheat. Okay. In conclusion, the first step, our system is superheat. Right? Our system is superheat. Because after you check between the vapor pressure at 100 degrees Celsius is 760 millimeters mercury, and then you calculate the vapor pressure. Right? You calculate the partial pressure equal to 526. This means the drop or dew point at this, which is dew point at 90 degrees Celsius. That's right. It's at 100. That's right. Vapor pressure greater than partial pressure means superheat. And then when it's drop to the liquid. Drop to the liquid, you can open the table by use the partial pressure, or the partial pressure is the vapor pressure. Is it 90? The difference is 10. And the second, if you cool the temperature from 100 to 80, calculate the percentage of vapor that's condensed and final composition of gas phase. Okay. First step, we have assume right for 100 mole of air steam. This include 10% water vapor, and another one is 90% of one dry. It's only the dry gas. It include water and dry. And the condition is 100 degrees Celsius. Pressure is 5260 mercury. And then you condense. It's condenser. After condenser, we get some liquid water, denoted as N1. Right? And N2 denoted as the humid air or gas. That's right, humid air. This is also include water and one dry gas. This include water and air. Okay, N2 is the total mole of air. Y is the mole fraction of water in vapor phase. 1 minus Y is the mole of one dry air. And the condition for this after cool, that's right, after condense, the temperature is 80 degrees Celsius. Pressure is the same. We condense at constant pressure. And this is saturated with water. Okay. If we analyze the degree of freedom, we have three unknowns, that's right, N1, N2, and Y. Three unknowns. We have only two species, water and air. Right? And also we have one Raoult law. Okay. One information from the Raoult law. Okay. The 3 minus 2 minus 1, you get 0 degree of freedom. You can use like the material balance or mass balance for that case. Okay. The first step, you have to use the information, the Raoult law. That's right. From the Raoult law, this is from the partial pressure equal to YIPI equal to vapor pressure. This is YIP equal to vapor pressure. We talk about the water. Okay, why water at this point? That's right. The condensation. Partial pressure at 80 degrees Celsius divided by P. What is the partial pressure at 80 degrees Celsius? You can open from the table B3. That's right. At 80 degrees Celsius, 80.0, 80.1, 0.2, 0.3, 0.4, 0.9. That's right. Pressure is 355.1. You get 355 divided by total pressure. You get the fraction of water in the output of the condenser. In this case, you know, right? You know why you can calculate 1 minus Y. Okay, you know composition of water, you know composition of one dry air. And then you can solve N1 and N2 from the real balance. In this case, you write the balance on dry air and balance on water or balance on total mole balance. For this case, we balance on dry air and total mole balance. For this case, there is no reaction, that's right, no consumption, no generation, and we assume the flow inflow out continually and equal. It's a steady state, input equal to output. The first step, we balance on the dry air. What is the dry air input? Dry air input, that's right, dry air input from this 0.9 multiplied by 100 mole. 0.9 mole bond dry air per mole total multiplied by 100 mole total, you get mole bond dry air. And output you have only one. This case, 1 minus Y multiplied by N2. That's right, 1 minus Y, you know Y. You can solve for it. Okay. 100 mole total multiplied by 0.9 mole bond dry air divided mole total. Get mole dry air equal to N2 multiply 1 minus Y. You know Y. You can solve for N2 equal to 96.5. And then the next step, we make the total mole balance. The total mole balance is input equal to output. The total mole balance, we have one input is 100 mole equal to N1 plus N2. You know N2 already, you can solve for N1. So for N1. And then N1 is the mole of water content. And the percentage condensation. The water content is 3.5 mole. What is water in the feed? Water in the feed is 0.1 multiplied by 100. That's right. It is 0 in the feed. And then you multiply by 100%, you get 35% condensation. Okay. The third one, we did not write the cooling, but we increase the pressure. We increase the pressure from what? We increase the pressure to 8,500 millimeter mercury. In this case, you check the state of first, because initially we know, right, the fraction of water multiplied by P or partial pressure is less than vapor pressure. This is the high pressure. That's why it's superheated. Okay. It's high enough to encourage to the become equality. Okay. And then you can calculate P saturated. P saturated for this equal to vapor pressure divided by mole fraction of water. Vapor pressure at 100, okay, this is at normal boiling point. More condensation is 760 divided 0.1, you get 7,600 millimeter mercury. Right? This for the saturated pressure. But for this case, we increase the pressure to 8,500. This is above saturation. What does it mean? We increase the pressure. There is some vapor condense to the water. Right? Condense to the water. We increase the temperature. We increase the pressure is higher than saturated. Okay, there are some condensation. The next step, you draw the balance and you base it 100 mole feed gas. You know 100 mole feed gas, you know composition of water and dry air. The compressor. You have two output. N2 is mole of air. This includes vapor water and dry air. And you know the temperature is 100. P is increased. We increase pressure at constant pressure and constant temperature. It is saturated. And N1 is mole of water content. It's also the same. That's why we have 1, 2, 3, 3 unknown. That's right. We have 3 unknown. We have 2 species balance and 1 Raoult law. You can solve for material balance. The first step, you use the Raoult law. That's right. Raoult law. In this case, the total pressure. That's right. You can calculate the mole fraction by partial pressure divided by total pressure. The partial pressure for this case 760 millimeter mercury, because it's vapor pressure. Vapor pressure divided by total pressure. Or the Raoult law is partial pressure Pi equal to Yi P. That's right. Equal to P star. For this case, we can calculate Yi from the P star divided by P. P star is mean the vapor pressure of pure water. And then you get the fraction 0.0894. You know why? That's right. You can solve material balance. You can balance on dry air. You can balance on water. You can balance on total mass. Is it input equal to output? There is no reaction. That's right. It's steady state. Okay, for dry air, input equal to output. Input dry air is 0.9 multiplied by 100 equal to N2 multiplied by 1 minus Y. 1 minus Y. You know Y, you can calculate for N2. Then you solve for total mass balance. 100 is equal to N2 plus N1. You know N2, you can calculate N1. And then you can calculate the percentage condensation. N1 is 1.2. 1.2 divided by total water in the feed is 0.1 multiplied by 100. You get 12%. That's right. Is it condensation based on increased pressure or based on decreased temperature, like previous the third question. And the last one, if there are some error, the experimental error, you should evaluate by possibility. It may be the error if the estimated value is differ from the natural value. What is the error? The condenser was not steady state. It may be the is it true steady state? It's not true steady state. That's right. If you measure the mass possibility because of system has not yet leveled out, not yet the steady state. Because more than the steady state, we have the time for startup, some time for startup, or at least the steady state. That's right. Okay. The second reason is maybe gas and liquid were not in equilibrium. That's right. Were not in equilibrium. The condensation actually occurred at a temperature below 100 degrees Celsius. That's right. And also the product stream were separate and reheat before merging. The second is maybe not equilibrium. Or the second is maybe it's not steady state because the steady state we have to start some time before steady state. And also Raw law does not apply. This is I will talk to you again for the next about the air water system. The three reason that is maybe why the estimate calculated value differ from the experiment or the experiment error is maybe due to the first one, the condenser is not real steady state. Mostly in the real system we have like pseudo steady state because there are some time before you reach the steady state. There are some time the unsteady state at the start on this startup. And the second one is maybe the equilibrium is not true, not equilibrium, possible. And the last one maybe law can apply for this because there are some the limit or the limit listen or the case assumption for the law. I will talk to you later why use the law. We talk about three slides before break. This we talk about the gas liquid system for one condensable for like the air water. We talk about the air water system. Okay, the saturation we refer to gas vapor combination, and if we talk about the humidity we refer to saturation also, but we talk about only the air water system. The saturation we the general gas vapor system. If you talk about the humidity, we refer only the air water system. We have 5 components about the humidity definition. Okay, the first one, relative humidity or relative saturation. That's right, relative humidity or relative saturation is SR or SR. Relative humidity is equal to partial pressure divided by vapor pressure of the fuel gas phase multiplied by 100. For example, if the humidity is 40, what is the humidity of 40? This means that the partial pressure of water vapor equal to 410 of the vapor pressure of water at the temperature. That is the relative humidity. And another one is molar humidity or molar saturation. Molar humidity or molar saturation or SM equal to moles of vapor divided by mole of vapor free dry gas. And what does it mean? It is the mole of vapor divided by mole of dry gas. Mole of vapor free, this means not include water. It's equal to Pi divided by P minus Pi. P is total pressure. And the third term is absolute humidity. Absolute humidity is also the same like the molar humidity because you use the molarity multiplied by the molecular weight. Side. SA equal to mole of vapor divided mass from mole to mass. That's mass of vapor divided mass of dry. Molar is mole of vapor divided mole of dry gas. Absolute is mass of vapor divided mass of dry gas. It's equal to Pi Mi divided by total pressure minus Pi of this multiplied by molecular weight of dry. And the last term we talk about the percentage saturation or percentage humidity. Is it equal to Sm divided by Sm star? Sm star. Sm is the partial pressure divided by Pi minus P. P minus Pi. And Sm star means vapor pressure divided by total pressure minus vapor pressure. Okay. For this case, if we If you are given any of these quantity for gas at given temperature and pressure, you can solve for the humidity, percentage humidity, absolute humidity, something. And also you can use formula to calculate dew point and degree of superheat. But before I will give you the example, right? This is we have the humid air at 25 degrees Celsius and 1.1 bar and 30% relative humidity is fit into the process. Less of 1,000 cubic meters per hour. Okay, determine what molar flow rate of water, molar flow rate of dry air, molar flow rate of oxygen enter the process. And the second one, calculate molar humidity, absolute humidity, percentage humidity, and the dew point. Okay, the first one, you know the percent relative humidity. Percent relative humidity, what is the definition? Relative humidity is the partial pressure divided by vapor pressure divided by 100. That means 100 multiplied by the partial pressure of water divided by vapor pressure of water. For this case, at 75 degrees of Celsius, you can open table B3. What is the vapor pressure at this? Vapor pressure is 289 millimeter mercury, and relative humidity is 30%. You know SR, you know vapor pressure, you can calculate partial pressure of water in the mixture of water and then you can calculate fraction of water vapor. Fraction of water vapor equal to vapor pressure divided, equal to partial pressure divided by total pressure. For total pressure is 1.1 bar, and then you convert 1.1 bar to be the millimeter mercury. Okay, you get this. Then you calculate fraction of vapor pressure equal to partial pressure divided by total pressure. Right? You get 0.105 mole water per total mole. And then you can calculate molar flow rate of wet air. Molar flow rate of wet air is the total, includes air and water vapor. You can use the ideal gas law. But if the pressure is lower enough to use the ideal gas law, okay, N dot equal to PV RT, PV equal to nRT, and then you can solve for N. Okay, you know the total pressure is 1.1 bar. You know the V dot is 1,000 cubic meters per joule, right? And R is 0.031831, that's right? Cubic meters bar per kilomole Kelvin. And you know the temperature is 25 degrees Celsius, and then you convert to Kelvin. And then you solve for molecular flow rate, that's right, or molar flow rate. It equals to 38.1 kilomole. And also you can calculate flow rate of dry air, flow rate of oxygen, and flow rate of water. Right? The first one you calculate flow rate of water. And you know amount of water. You know amount of water. What amount of water is 0.105 kilomole water per kilomole of total. For this case, you know the kilomole of total is 38. That's right, 38 is the mole of air. But in this air, consists of 0.1 kilomole water per kilomole. You can calculate this N water and N dry air. In dry air, the mole fraction of one dry air equal to 1 minus 0.105. This is the mole of water. Multiply this with total mole, you get flow rate of one dry air. And the last one, oxygen. The oxygen. Oxygen, how to calculate this? The oxygen included in air, that's right, in dry air. For this system, we have two, right? Water and air. Okay, you calculate water, this. Calculate air in this. Now oxygen. Oxygen calculate from air. That's right. From air, you know 21% mole of air. Right. sorry, 21% on oxygen in air, because air we mostly have two components, nitrogen and oxygen. And you know the composition of oxygen in air is 0.21 kilomole air per kilomole bond dry air. But for this case, you know bond dry air is 34. You can calculate oxygen. Okay. This is the first question finished. And then the second question, molar humidity, absolute humidity, percentage humidity. The molar humidity is equal to partial pressure of water divided by total pressure minus partial pressure of water. In this case, you know partial pressure already. You know total pressure. And then you calculate molar humidity. And then you calculate, right, absolute humidity. That's right. The absolute humidity is the same molar, but it also for mole to mass. In this case, you know 0.117 mole water per mole bond dry air. You change it by conversion from mole to mass by molecular weight. Okay. 0.117 kilomole water per kilomole bond dry air. And then you multiply by molecular weight of water and divided by molecular weight of the air. That's right. Molecular weight of water is 18 kilogram water per kilomole water. And dry air is 29 mole of kilogram of dry air divided by mole of dry air. You get this is absolute humidity. And then calculate, right, the percentage humidity. Percentage humidity is the molar humidity divided by SM. That's right. SM is molar humidity divided by molar humidity at vapor pressure. First step, you have to calculate S star M. S star M is the vapor pressure divided by total minus vapor pressure. Vapor pressure, that's right, you know already, 189. Total pressure, vapor pressure, you get S star M. Percentage humidity equal to 100% multiplied by molar humidity divided by molar humidity at vapor pressure. Molar you know already. This is the you get 21.7. And the last one, the dew point. For this case, you use law. The dew point you calculate from the partial pressure at 86.7 millimeter mercury, which equal to vapor pressure. And then it is the vapor pressure, and then you can interpolate this from the table B3. Get dew point is 48.7. And open the table B3. And you can by yourself. We'll stop for this and we'll continue for the next the multiple gas liquid system. Previously, we talked about the multiple phase, vapor phase, and gas phase, but we about only one condensable. Only water can condense. The next step, we talk about the multiphase, maybe more than one condensable. See you for the next.